But I'll just set up each of the integrals because the hard part really is just finding the bounds, right? That's the hardest part of all of these. Okay, so this first one, here we go. It says evaluate the integral where omega is the triangular region bounded by the y-axis and the line y equals 1 and y equals um, 1/2 x. And you guys don't have audio. Testing, 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 testing.
Gone.
Okay, that's better. There we go. Hopefully it stays like that. Okay, so we want to evaluate this integral. Um, so the first thing I need to do this is I need the bounds. So the way I do this is I set up, or I need to draw the region. Okay, so here we have the line y equals 1/2 x. That's going to look something like this. And we have the line y equals 1. And the y-axis, right? So that's here. It's the vertical. So this is the region we're interested in. Okay. Now, first I integrate this with respect to x. Okay, so what I'm going to do,
Mic off. Mic on.
what I'm going to do is I'm going to pick a value of y. It doesn't matter which one. Okay, I'm just going to draw a slice across my region that I'm interested in. Okay, so I pick this and I go in the x direction. Okay, so I'm integrating with respect to x. I'm going to draw a slice in the x direction. So now I ask, so I'm integrating this. What is the minimum value of x? That's going to be here, right? So that's going to be 0, right? This is x equals 0. And then what is the maximum value of x? So this is the line y equals 1/2 x, or equivalently, x equals 2y. So the maximum value of x in this case is going to be x equals 2y. Okay, now I need to integrate that with respect to y. So I want to cover my region with these slices, right? So how far down do these slices go and how far up do they go? How far down do they go? They go down to y equals 0. So I'm going to start that at y equals 0. And they go, how high up do they go? They go up to this line y equals 1, right? We have slices all the way up to here. So this is up to 1 dy. So this is what I would integrate. And I wouldn't do this with respect to y first because I don't know how to integrate e to the y squared. But if I integrate this with respect to x, it comes out nice and simple. Okay, next one. So the next question is this one. Oh my gosh. Okay, evaluate sine of x squared plus y squared dx dy, where omega is the annular region between the two circles. So real quick question. Uh, should I use polar, cylindrical, um, or spherical? Right, so it's going to be polar coordinates because this is just a 2D thing, right? We just have x and y. There's no z, right? So I see x squared, y squared. That makes me think something polar. Since it's just 2D, polar is the only option. So I know that, let's see, if I just write that integral, I can convert that real quick. So that's going to be sine of r squared, right, because x squared plus y squared is r squared, times r dr d theta. Now, to get the bounds, first thing I do is I draw a circle. Or sorry, I draw the region. So the annular region. So an annulus, for those of you who haven't seen that term before, is like the shape of a washer. Okay, so it gives us two circles. It gives us this one and this one. So this one we got to be a little bit careful. So x squared plus y squared, what is the radius of this inner circle? What do you guys think? Radius of the inner circle is what? Half pi. So that's the tricky part. It's not. Because remember, x squared plus y squared equals r squared. It's going to be the square root of pi over 2. Right. So here, the inner radius, right? So this, if I draw a radius, I draw this some radius. The first bound that I come to, it's going to be the square root of pi over 2. And then I keep going along that same direction, and the second radius that I get to, or the second edge that I get to, is going to be square root of pi. Now I have this slice, and I want to use this slice and rotate it in the theta direction, right, clockwise, and I want to be able to cover this entire region. So if I start at 0, theta equals 0, I need to rotate this all the way around. So that means that theta is going to go from 0 to 2 pi. Okay, and that's going to be how you solve this. And then you can solve this doing a u sub for r squared, and it shouldn't be terribly hard from there. Okay, next one. Okay, so again, I only have two coordinates, x and y, and I see x squared plus y squared, so this makes me think polar. Okay, so if I rewrite this, this is going to be 1 over 1 plus r squared times r dr d theta. Now, I need to know the bounds. Okay, so this is x. So here we have x goes from 0 here to x equals root 4 minus y squared. So if I square both sides, I can rewrite this as x squared plus y squared equals 4. Right, so this is the positive part of a of a circle, right? It's a half circle with positive x values. Right, if there was a negative in here, we would get the other half. Okay, so that's this bound, and then so we know that x starts here, starts at 0 and goes to this curve, and then it starts at minus 2, which is going to be down here. Oops. It starts at minus 2, which is down here, and then they go all the way up to 2, which is up here. So the radius is going to go from 0, it goes from 0 out to 2.
Mic off. Mic on.
Okay, so we have here, right, the radius is going to be all of these values from 0 out to 2. So the radius goes from 0 to 2, 1 over, it's going to be r over 1 plus r squared dr. And theta, we can do this in a number of ways, but let's start here at minus pi over 2 and swing all the way around to pi over 2. Right, so r goes from 0 out to theta. If the inner bound was flipped, 1 second while let's see. From minus pi over 2 to pi over 2. Okay, what do you mean by flip? Do you mean this inner bound, or do you mean this one right here? So the question is, if the inner bound was flipped, would it be the other side of the circle? So the negative side of the circle would be from minus square root of 4 minus y squared to 0, right? This curve is that curve, right? So the negative. And then the whole circle would be from here to 4 minus y squared. Okay, d theta, and that is my integral that I would solve. Next question. Let's see. So number 4. Here we go. Okay, so here, right, this is written as integral of sine pi of x cubed dx. I don't know how to integrate this with respect to x, but if I integrate it with respect to y, there's a chance that I might be able to actually do it. Okay, so what I'm going to do is I'm going to flip the bounds. I'm going to leave it in terms of x and y, but I'm going to flip the bounds. So this is going to be integral sine of pi x cubed dy dx. Okay, so again, like usual, I start drawing the region. Okay, so the line x equals root y, what does that look like? Well, if I square both sides, that's the same as y equals x squared. But, it's going to be positive. So here, that's going to look something like this. All right, so this is the line x equals root y, or y equals x squared. So here, this is written with respect to x. So that means that this is the minimum value of x. So we start here, and we keep going this way until we get to the line x equals 3. That's like this. Right, so that's a bunch of strips like this. Right, and they start at 0, and they go up to 9. So that's this whole region. Right, so this is x equals 3. So now, instead of vertical slices, I want to do this in terms of, instead of horizontal slices, I want to do this in terms of vertical slices. So I'm going to draw a vertical slice to integrate with respect to y first. And where does that vertical slice start? It starts at 0, at y equals 0, and it goes up to the maximum value of y equals x squared, right? So how high up it goes depends on where I'm at, but however high up it goes, it's just x squared. And that I can integrate from 0, right? I have all of these slices, and I'm going from 0 up to 3. And then you can integrate this and do a u sub, and it becomes a lot easier. Okay, why are the shaded part not on the other side? You mean like that? No. Oh, why is it not above? Oh, okay. So let's go back to how we found which region it was in the first place. Okay, so I know that my curve is going to start, so here I'm integrating with respect to x, so I'm going to be drawing horizontal slices, right, in the x direction, and these slices are going to start at y square root of y, right? That's this curve here. So it's going to start here and go this way. So basically, I know that my region has to be on this side, on the right side of this curve. Okay. Yeah. So it all comes from how I drew it to begin with. Okay. Um, once I flipped it, I'm describing the same region. Okay. So once I flipped it, I didn't change anything other than which way I was drawing the slices. I'm still covering the same region. So yeah, drawing the region is important. Okay, next question. Um, that's this one.
Mic off. Mic on.
Okay. Okay, so dz dy dx. So should I convert this to spherical or polar? Oh, sorry, spherical or cylindrical? What do you guys think? Okay, I hear cylindrical. Okay, I see a good number for cylindrical. Okay, I could do this in any number of ways, but um, let's at least draw the region first. Okay, so um, if I do, actually, I'm going to do it both ways. I'm going to do it both ways. So when I worked this problem, how did I do it? I did this one. I did this one in spherical. Okay, but let's do it both ways. So cylindrical coordinates, let's see, so we have z is z. So let's at least rewrite these bounds. So that's from okay, actually, so we have z goes from 0 to z equals square root 4 minus x squared plus y squared is going to be r squared. Okay, so these are the bounds on z. Okay, and then here I can actually draw the xy part, right? So this is going to be the top half of a circle, right? For y equals 4 minus square root of 4 minus x squared. So that's like this. And this is the bottom half of a circle. Okay, and then that goes from 0 to the x coordinate goes from 0 to 2. So in the xy plane, it's describing this. And then what does this describe? Well, actually, let me look at it this way. So if it was 4 minus x squared, if we look in the z, let's just say this is x, so y is 0. If y was 0, this would be 4 minus x squared, which would be this shape here. Okay, and it's going to be kind of symmetric since it's x squared plus y squared. It's going to be the same no matter what direction we're looking in. So really, with this shape, it's the top half of a sphere. Okay, so in this case, I don't know that cylindrical is necessarily the best. I did it with respect to spherical, but we can keep going this way. So we know that these are the bounds on z, and then so right because that goes from here up to here, right? The radius is 4 minus r squared. So I have the integral from 0 to square root 4 minus r squared. Why is it only the right side? So here, right, the x coordinate starts at 0 and goes up to 2. So here it starts at 0 and we're doing slices all the way up to 2 here. Okay, so if I'm converting to cylindrical, this becomes r dr, and then, sorry, no, that's dz. And then I need to describe this circle, so r can go from 0, r can go from 0 out to the outer circle. So r goes from here out to here. So r goes from 0 to 2, dr. And then theta, right, we only want this right half, so that's going to go from here all the way around. Theta will go from minus pi over 2 to pi over 2. Okay, so if I did this now in terms of spherical coordinates, okay, what do I have? I have z that's bigger than 0, but also on this side I have that z goes all the way up to the curve z equals square root 4 minus x squared minus y squared. So I square both sides, I can rewrite this as rho squared equals 4, meaning that rho equals 2. Right, so here rho is 0 and here rho is 2, just like r. Okay, so I can integrate with respect to that. I have integral from 0 to 2 of, so there was nothing here before. How did I get the pi over 2? 1 second. Rho squared sine phi d rho. So over here, we want just this, the right half of the circle, right? Because we want only where x is positive. So if I'm trying to sweep this out in the theta direction, if I start here at minus pi over 2, I can rotate around to pi over 2. Okay, so back down here to spherical coordinates. I was, so we integrated this with respect to the radius. Okay, so now the phi needs to go from vertical down to the xy plane. So phi is going to go from 0, right, that's the vertical, down to the xy plane, which is pi over 2, right, that's an angle of pi over 2.
Mic off. Mic on.
And then theta is going to be the same because in the xy plane, we have exactly the same region. So this is minus pi over 2 to pi over 2. So that's how I set it up. I saw the z equals square root of 4 minus x squared minus y squared. So I thought this right away, right, because in spherical coordinates you have rho squared equals x squared plus y squared plus z squared. Right, so whenever you see x squared plus y squared plus z squared, that should make you think spherical coordinates. And if you just have something like x squared plus y squared, I would think either cylindrical or polar. Will it be 0 to pi over 2 most of the time? 0 to pi over 2. No, there's an example later on, the last question, where it's not. So we'll see that here in just a little bit. Okay, next question. Unless there's any more questions on this one. Okay, so next question. Oh, this one was fun. Okay, so it tells you to swap the order of the integrals. This is not easy to visualize or draw. Okay, so we want to swap the order so that it's dy, dx, dz. So let's try to think about what this region looks like. So here I know that z goes from 0 to 4 minus y squared. So if I just do z and y, 4 minus y squared is a downward facing parabola like this. Okay, and notice that these bounds here, they don't depend on x, right? So no matter what value of x I have, this shape is going to be the same. So this is going to look kind of like a folded sheet of paper almost. Okay, so y goes from 0 to 2, so it starts at 0 and goes out to 2. That's where it intersects, right? When z is 0, yes. So this is the region we're interested in, right? From 0 to 2. And then x, so coming up out of the screen, x goes from 0 to 1. So really it's this shape, but extended straight up out of the screen from 0 to 1. So I want to rewrite this first as an integral. I want to first integrate from 0 to y. Oh, sorry, with respect to y. Because that's what the question asks, right? dy. So this is the curve z equals 4 minus y squared. I can rewrite this as the curve y equals square root of 4 minus z. Okay, so if I want to first integrate with respect to y, so I draw a slice in the y direction. Okay, and where does that start? It starts at 0, and it ends at y equals square root of 4 minus z dy. Now it says I want to integrate with respect to x. Well, this one's easy because I know that the x, if I just take the slice, it goes from 0 and it comes straight out to 1. Nothing changes. Like this. And then I need to integrate with respect to z. So now I have kind of like these, it's like a plane. So I did a slice like this, like a little line, and then I pulled that out in the x direction to make like a little plane, like an actual slice. And then I want to stack these slices up from z equals 0 all the way up to the maximum value of z here, which is 4. So that's going to be integral from 0 to 4 dz. So this one's kind of hard because you have to imagine the x-axis kind of coming out in this direction. But since it's just 0 to 1 and nothing depends on x, it's not terribly difficult like that. Yeah, and this is all you had to do for this question. Next question, unless there's any questions on that one. Okay. So the next one is cylindrical coordinates. We didn't have to evaluate 6. Well, no, because we don't know what the function is. Right, it just says f is some function. So it just says give an equivalent integral. So all it was asking was for you to rewrite the, change the order of the integrals. So similar to this one, it just says rewrite in spherical or in cylindrical coordinates. Okay, so like I said in the 2 questions ago, if I have x squared plus y squared, right, that's going to be r squared. So if I have x squared plus y squared, I should think polar or cylindrical. If I have x squared plus y squared plus z squared, I should be thinking spherical. So here, right, I might have something spherical. Should just drop my pen. Okay, so I might have something, that might be useful spherical, but down here, I only have x squared plus y squared. I should be thinking polar or cylindrical.
Mic off. Mic on.
Okay, so it tells us though cylindrical. So we integrate this, and let's convert this to cylindrical. So that's going to be 1 over r times r dr d. Actually, let's do dz dr d theta. Okay, so let's draw this. So this is actually very similar to what we had 2 questions ago. This describes the top half of a sphere, right? So again, if you imagine this is x and y is 0, that's going to be the top half of a sphere, right? Because this would be 9 minus x squared. But it's going to be kind of curving down in all directions. It's the top half of a sphere. It's going to be really symmetric if I rotate this around. Okay, and then if I'm looking straight down on the z-axis, I have this curve, 9 minus x squared, and then I also have the bottom curve, negative root 9 minus x squared. And then I know that the x-coordinate goes from negative 3 to 3. So that means that these slices are starting at negative 3 way over here, and they go all the way across to here, to 3. Okay, so basically this is just the top half of the sphere. And actually, since with a radius 3, right, this has a radius of 3. And actually, if you wanted to evaluate this, right, the r's cancel out, and we're just integrating I'm sorry, never mind. Never mind about that. But okay, so first we go z. Z goes from 0 up to, that doesn't really change, 9 minus r squared. Okay, and then what about phi? So, not phi, r. R, again, it goes from 0, and we want all of the radius within this range. So the minimum radius is going to be 0, and the maximum radius is going to be out here at 2, right? It doesn't really matter what angle or height it's at, but the maximum radius is going to be 2. And then for theta, we look in the xy plane, and we need to rotate this all the way around. So we go from 0 to 2 pi. And that's my integral. So this is actually yeah, that actually wouldn't be fun to evaluate, because when these cancel out, you integrate, you have to integrate this with respect to, yeah, you have to integrate square root of 9 minus x squared, and that's like trig sub. So actually evaluating this integral would be kind of hard, unless maybe, yeah, unless maybe you swapped the bounds, but that just sounds like more work than needed. Anyways, that's all you had to do. So why is the top half of the xz plane? Okay, so here, it's going to be the top half of the YZ plane also, right? So the thing that I have is that z starts at 0, right? The minimum value of z is 0. So it's going to be the top half of the, or the, it's going to be above the xy plane. Right, so it goes from 0, and then it goes up from there to whatever curve this is. Is it max r value 3? Yes, it is. That should be a 3. Okay, any other questions on this one? Okay, last one. So first thing I see x squared plus y squared plus z squared. I should think spherical coordinates. And it even had spherical in the question. So if I rewrite this, this is going to be 1 over rho squared times rho squared sine phi d rho d phi d theta. Okay, so now what do these look like? So this, it's a cone. It's going to look like this, but rotated all the way around the z-axis. Right, so it actually looks like a cone. And then x squared plus y squared plus z squared equals 25. That's going to be a sphere with radius 5. So I'm interested in this region here. Okay, so let's start describing these. So I know that the radius, rho, is going to go from 0 all the way out to 5. Okay, so that's an easy one to start off with. So I have integral from 0 to 5. The rho's cancel. I have sine phi d rho. Okay, so here's the example I was mentioning earlier where phi, I'll do that one last. So theta, if we're looking down at this cone, it's going to go all the way around. All right, so theta is going to go from 0 to 2 pi. Okay, now the hard one is the phi. So phi goes from 0 to this angle here. Okay, so real quick, this when I draw this angle, that corresponds to this slice here, starting from the origin and just going in the positive x direction, and that's what we rotate around. I could start from here and go all the way over, and that would correspond to this. If I did that, I would only have to go halfway around. But I'm not going to do that. I'm going to start at 0. It's just easier to keep track of. Okay, so this goes clearly, it starts at 0, but where does it end? So what do we know about this? I'm going to convert this right here, the into spherical coordinates. So we have z, which is rho. Actually, if I square both sides first, I have square both sides. I have cosine phi equals x squared. So x was rho sine phi cosine theta. So I square that, squared, plus y, which is rho squared sine squared phi sine theta squared. Okay, so I can factor out the rho squared sine squared phi, and I get sine squared theta plus cosine squared theta. So what I end up with is rho squared cosine squared phi equals rho squared sine squared phi. Okay, so if I assume for a second that theta is, or not theta, rho is not 0, I can cancel this on both sides. And I have this. Hold on one second.
Mic off. Mic on.
Okay, so what I have is this. So if I take square root of both sides, I have, actually, if I subtract this, I have sine squared phi minus cosine squared phi equals 0. I can factor this. Sine phi minus cosine phi, and sine phi plus cosine phi equals 0. And that lets me conclude that sine phi equals cosine phi, or sine phi equals negative cosine phi. This happens at pi over 4. This happens at minus pi over 4. So that tells me that this angle right here corresponds, or this line right here corresponds to phi is, let's see, this is true when phi is equal to pi over 4. So this is the line pi equals pi over 4. This would be negative pi over 4. So I don't really care about this one. I'm just going from 0, and it's going to go to pi over 4. And that's my integral. Okay, so I hope that's a lot of practice on these. I know the homework was a bit long, but hopefully you're good on these, because after this we're going to be moving on to the next topic, which you guys started, which was line integrals and more just like vector calculus stuff. So hopefully you're good on this. Any questions about this, the homework? If not, I'm going to go ahead and stop here.